Okay, so in this chapter, we talk about the performance of the circuit. So, and we typically have two parts in this chapter regarding the performance of the circuit. The first part was the speed or the delay. So in the first part, we discussed the delay of the circuit, and we talk about the model, the mathematical model. Basically, we use the linear delay model to estimate the delay. So, and the delay is one of the very important factors in the operation and design of a circuit. So it basically determines the speed of the circuit. Okay, and then the second part in this chapter, we would like to focus on the power consumption or energy consumption of the circuit or the VLSI system. Okay. Power or energy has become more and more important, especially in handheld or battery-driven devices, such as like cell phone or your tablet or some other wearable devices. Okay, so and some like IoT applications. So power and energy consumption of the circuit has become more and more important. So in this part of this chapter, we will give you a basic idea of how the power is consumed in the circuit, or what kinds of approach we might be able to use to reduce the power consumption of the circuit. That will be the main purpose of the second part. Okay, so before we get into the power consumption of the circuit, so we will like to review some basics related to power or energy in circuit and in electronic circuit. And mostly those topics have been discussed in the course like fundamental circuit or introduction to electronic circuit course, but we would like to review that. Okay, so first of all, give you a high-level overview. So the power dissipation or power consumption in the CMOS circuit comes from two major components. The first one is called the dynamic power, and the second one is called static power. So dynamic power is related to the charging and discharging of low capacitors, as well as come from the short circuit current when both PMOS and NMOS networks are partially on. So basically that means the dynamic power comes from when your circuit is operated. So for example, if your circuit is designed to perform the multiplication of two numbers, and then when you perform the multiplication of those two numbers, you have some circuit switching, like from a certain bit from 1 to 0 or certain bit from 0 to 1. And those 1 to 0 or 0 to 1 will cause the charge or discharge of the low capacitors and then results in the power consumption. So this part of power consumption is considered as dynamic power. And another power of power consumption of the circuit comes from the static power. The fundamental idea of static power is the power is consumed even though the circuit is idled or the circuit is not operated. Okay, so this part is called the power consumption. There are several sources of power consumption, static power consumption, such as sub-threshold current in the MOS, the leakage current through reverse bias diodes, or tunneling current through the gate oxide. Okay, so basically, that means even your circuit is not used, even the circuit is not operated, you still have the power consumption. We call this part the static power. Okay, traditionally, the majority of power consumption of a circuit comes from dynamic power. Okay, so that's the especially in not so advanced manufacture process. However, with the more advanced manufacture process, the ratio for static power has become increased. So that means traditionally, if you want to reduce the power consumption of the circuit, we usually focus on reducing the dynamic power consumption because that's the majority of your power consumption in the circuit. But recently, when we are implementing the circuit with more advanced manufacturing process, there are more and more work focusing on reducing the power consumption, especially for the static power, because the static power has become the dominant factor of power consumption in the circuit. Okay, so but the bottom line is, if you want to have a low power circuit design, then you probably should reduce the dynamic power and the static power at the same time. Okay, so that's the ideal case. So in the bottom, you can see the P total. That means the total power consumption equals to P static plus P dynamic, which is the static power consumption plus dynamic power consumption. Okay, and the P dynamic, which is the dynamic power consumption, equals to switching power. So the capacitance, the charging and discharging of the capacitance, plus P short circuit. That means the circuit current when both PMOS and NMOS networks are partially on. And on the right-hand side, you can see that the P static power, which is the static power consumption of the circuit, equals to subratio, leakage, junction power, tunneling, and several other sources, and times the VDD, the supply voltage. So we will show the detail later on. So that means the supply voltage VDD also plays an important role in power consumption of the circuit. So we will show that later on. Okay, so then before we get into the power consumption of the electronic circuit, we would like to give you some fundamental review about the power and or the energy. Okay, so let's consider the power dissipation, especially dynamic power dissipation, which means the power comes from the circuit switching, or you really operate your circuit. So assume you have a capacitor, and then the energy stored in the capacitor is formulated as follows. So EC is the energy stored in the capacitor. Capacitor is the integration from the integration over time from 0 to infinity over I of t times V of t, right? The instant current times the instant power. Okay, and since I of t is equal to the derivative of V over T times the capacitance CL, so this formula can also be written as the second formula. Okay, and since if we integration over the voltage from 0 to supply voltage of VDD, then the formula can be described as VDD squared times CL divided by 2. So this will be a very important equation, and we'll use that equation a lot later on. Okay. And then when we consider the energy delivered from the power supply, we have the similar formula, but we don't have the 1/2 equation here. So that means basically we can describe the energy dynamic power of a gate, the P dynamic power of a gate equals to alpha times CL times VDD squared or times F. Okay, so now we can take a look at this one by one. So CL is basically the capacitor value of the circuit, and VDD is the supply voltage. Frequency is F is the clock frequency of the circuit, and alpha is known as we call activity factor. Okay, so this activity factor is interesting because it is a kind of a term of a probability. Okay, so it is a probability. The alpha is a probability that the circuit node transition from 0 to 1 during a clock cycle. So that basically means, think about this, because here we are considering the dynamic power, right? And dynamic power basically comes from the switching 0 to 1 or 1 to 0 of a node. So that means if there's no switching, I mean if there's no from 1 to 0 or 0 to 1, then then you don't have dynamic power, right? Because the dynamic power basically comes from the circuit switching. And then another question is like, is your circuit always switching? Is your circuit always switching? That is not always true. That means if you have a circuit, like for example, for the purpose of multiplication, that doesn't mean this multiplier always performs the operation of multiplication, right? You only perform the multiplication when, for example, you have a input data, or when you have when your input data is updated. Otherwise, if your input data is not updated, or you don't have input data, or especially a new input data, then the multiplier is not operated. So that means the operation of the circuit is not deterministic. That means we cannot assume that the circuit is always operated. So that means the dynamic power is not always consumed. Okay. So that means we times this alpha as a probability. That means statistically, what's the percentage of your circuit is operated or is active. For example, if alpha equal to like say 80%, that means 80% of the time your circuit is operated, and then you consume the dynamic power. On the other hand, if alpha is equal to like say 30%, that means only 30% of the time your circuit is operated and you consume dynamic power. Okay, so we use this alpha to kind of like modulate the when or the ratio of the circuit is operated, and to come up with a little bit more accurate estimation of dynamic power. Okay, so that's the idea. So we will talk about this alpha more in later slices. Okay, but this P dynamic equals to alpha times CL times VDD squared times F is one of the very important equation in VLSI circuit, because all the low power technique basically comes from this equation. Okay? We will talk about this more. Okay, so then we can take a look at this dynamic power dissipation here. So if we write down this P dynamic equals to alpha times CL times VDD squared times F, okay, so then we can kind of observe this equation. Okay, so first of all, the CL is the capacitance of the node, so it's basically related to the manufacture process of the node and how you implement this circuit. Okay. Secondly, the activity factor, which is the alpha here, heavily depends on the particular task being executed. So, for example, you have cell phone video processing, multiplication or division, addition, or subtraction. Okay. So in other words, without specifically saying that which kind of application you are using, it's very difficult to have a very accurate number of alpha, because that's the probability. So alpha is very application specific. So that means if you want to know what the values for the alpha are, you need to know what kind of application you are executed, and that may be different. So for example, the alpha for a cell phone might be different from alpha for video processing. Okay, so that's very application specific. And then, so if we don't look at alpha, because that's kind of probability and application specific. If you don't look at CL, because that's mainly related to the manufacturer, then we have two factors, F and VDD, right? So based on this F and VDD, you can know that if you reduce the VDD, which is a supply voltage, you can reduce the dynamic power, right? Because especially this is a VDD square. So to reduce the VDD is one of the approach you can try to reduce the power consumption. Okay, so from the low power point of view, you want to have a minimum VDD, right? The VDD is as low as possible because you can reduce the power. But On the other hand, you need to have the sufficient VDD to drive your circuit. Okay, so that means you cannot reduce the VDD to below certain threshold because you need that kind of threshold voltage to drive your circuit. Okay, so that's the kind of like two extreme. You want to reduce the power, then that means you want to reduce the VDD. But on the other hand, you want to drive the circuit, so you want to maintain the VDD to be above certain threshold. Okay, so that's how you decide the value of VDD. Okay. Secondly, F is the frequency. So in terms of the low power design, you want to reduce the frequency, right? Because if you reduce the frequency, which is F here, then you reduce the dynamic power. Okay. However, frequency also represents the speed. If you reduce the frequency, that means you reduce the speed, right? So that is also a kind of dilemma here. You need to decide let's say a good frequency so that you can find a balance between the speed and the power consumption. Okay, so that's how you decide on your frequency. Okay, so that's one of the reasons why that for handheld devices like your cell phone, the operating frequency is usually lower than the station kind of devices like your PC. Okay, so the CPU or the processor used in your personal computer usually operates at a higher frequency than the CPU that is used in your cell phone, and mainly because of the power consumption issue. Okay, because if the CPU or other devices in your cell phone operates in a way too high frequency, then according to this formula, you will increase the power consumption, and then you will run out of your battery very quick, and then you really need to recharge your system, right? So this equation can tell you one of the reasons why your handheld devices cannot be operated in a very high frequency, mainly because of the power consumption issue. Okay, so this equation tells you that clearly. Okay, so that's the basic idea of dynamic power. So let's take a look of this activity factor. Okay, so again, this is a probability. So we don't exactly know the value. We can only estimate. Okay, so again, similarly, if you remember when we talk about the delay of the circuit, because we cannot, or it's very difficult to have a very accurate number for the delay in the circuit. So we usually build up a model to estimate the delay of the circuit. The similar case here is very difficult to have a very accurate activity factor alpha. So we kind of build up a model to estimate activity factor. Okay, so the way we define that is like this. We define we have a node called I, so node I here. So Pi is the probability that this I is 1. Okay, the node of I is 1. And Pi bar is the probability that the node I is 0. Okay? And then the activity factor alpha I for the node I is Pi, which is the probability that the node is I, times Pi bar, which is the probability that the node I is 0. Okay? And so let's assume if we have a completely random data, so that means for one bit, you have 50% of being 1 and 50% being 0. So in that case, Pi will equal to Pi bar will equal to 0.5, 50%, right? So then alpha I will be Pi times Pi bar, which is equal to 0.5 times 0.5, which is 0.25. So if you have a completely random data, the P will be 0.5 and PI also 0.5, and the alpha will be 0.25. Okay, so that's for completely random data. Okay. However, in the electronic system, the data is often not completely random. Okay, so for example, if you want to do a calculation of, for example, multiplication or the other operations, then let's assume you have like 64-bit words. Okay, and according to the statistic, the lower bits of the 64-bit word is usually more commonly used than the upper bits of the 64-bit word, right? Because in most of the time, or in most of the multiplication operation, you usually only involve with the lower parts of the bits in a word, right? So that means the probability or the activity factor alpha for the lower bits of in a word will be different from the activity factor in the higher upper bits in a word, right? So it's not completely random. Okay, so there are actually quite a lot of research going on to design the low power system or low power circuit based on the analysis of the activity factor for different bits in different words. Okay, so that's one of the research topic actually. Okay, and another typical issue is like data propagating through N and OR has lower activity factor, and depends on the design, usually is like 0.1. So that's the fact related to the N gate and the OR gate. Okay, so then let's give you a example here. Okay, so we can use this probability to study we call the switching probability. Okay, so the switching probability means the output probabilities of various gates as a function of their input probability. Okay, so for example, if you have a 2-input AND gate, okay, and then the input probability for one input will be PA, and another input called PB, and the output probabilities for this kind of gate will be PA times PB. Okay, and similarly, if you have a 3-input NAND gate, then the probability of the 3 inputs will be PA, PB, and PC, and the output probability will be PA times PB times PC. Okay, so that's the output probability for the N or for the 3-input AND gate. And for the OR gate, let's do this. Okay, so if we have an OR gate, let's say A plus B, okay, and that's actually equals to A prime times and B prime, right? Because according to the De Morgan's rule, right? For De Morgan's rule. So then the probability of A prime will be PA bar, right? Okay, because the probability for A being 1 is PA, then probability for A being 0 will be PA bar. So A times B prime, the probability of B prime will be PB bar. PB bar. Okay, so this is the probability for B being 0, so PB bar. But we have a complement, right? So that means if you do this, that's the probability of A being A prime times and B prime. Okay, but what we want is the inverse of this probability, right? Then when you want to calculate the inverse of probability, you usually use 1 minus the probability. For example, this probability is 10%. Then the inverse of this probability will what? 90%, right? 100% minus 10% will be 90%. Okay, so that's how you get this one here. That's how you get this one here. Okay, so the output probability for the all two input OR gate will be 1 minus PA bar and PB bar. Okay. Okay, and then if you have a two input NAND gate, so here you have two input NAND gate. So NAND gate means A, let's assume you have input A times B, and then you have a complement, right? You have a complement here. So the probability of A being 1 is PA. The probability of B being 1 is PB. And you have a complement here. So you have a complement here, so that's 1 minus, right? So this complement will represent this 1 minus. So 1 minus PA and PB, so that's why you get this. If there are two input NAND gates, that's 1 minus PA and PB. Okay? Okay, so and then if we consider the NOR gate, right? If we consider the NOR gate, so NOR gate is A or B complement, right? And this equals to, according to the De Morgan's rule, that is equals to A prime dot B prime, right? And then the probability of A prime is PA bar, and the probability of B prime is PB bar, right? So that's why you get this, the output probability for the NOR gate. Okay, so that's why you get this. Okay, and then the XOR gate is straightforward because XOR basically is A B prime plus B prime A, right? So you just apply this. Okay, so that's how we get this probability here. Then we can use this to calculate the probability of a circuit. Okay, so let me show you an example here. Okay, so let me try to do this. So this. Let's copy the table here so that we can calculate. Okay, so let's do this calculation. First of all, you have a NAND gate here, right? You have a NAND gate here. Okay, so and we know the probability. Let's assume we have the input probability of 0.5. Okay, so PA is 0.5. PA equals to PB equals to 0.5, right? Then that means what? That means equals to PA bar equals to PB bar also equals to 0.5, right? Okay, so that's how we get this. Okay, so then let's say take a look. This is a two input NAND gate. So we take a look at this two input. Oh, sorry, no, not this one. The two input NAND gate here. Okay. So the output probability here, equals to 1 minus PA times PB, right? Equals to 1 minus 0.5 times 0.5 equals to 0.375, right? Then that is the probability of 3/4. Okay, 0.75. Okay, so but we want to calculate value of alpha, right? So how do we calculate the value of alpha? Alpha equals to P times P bar, right? And for this case, N1, the P is 3 times over 3/4. And what's the P bar? P bar is 1 minus this, right? So equals to 3/4 times 1, right? 1 minus 3/4 equals to 16 here, right? So that's how you get this alpha here. Okay, make sense? Okay, so similarly, we have this 16/3 here. Okay, so now you know the alpha and the P for this. Now, then we want to take a look of this gate. Okay, so what's this gate? So this gate actually is, let's say, assume the input will be here A. Let's say, no, let's say this is X. No, we can say Y. So this is A here. So let's say this is A. This is B. Okay. So this is Y equals to, so this Y equals to A, Y, B, Y, right? B, A prime, B prime. And then, oh no, it's just end. Right? Okay. And then okay. So then we want to calculate the P here, and we want to calculate the alpha of this gate and the output Y here. Okay. So we know that this will be equals to A plus B and then prime, right? Correct, right? According to the Democracy rule. So this is what? Actually, this is a NOR, so this is a NOR gate, right? So this is a NOR gate. And this is a two input NOR gate. So this is a two input NOR gate. Okay? And according to this table, the two input NOR gate will be the probability of A bar and probability of B bar. So that means when we want to calculate the probability here, this will be equal to PA bar times PB bar then equals to, so what's the PA? So PA is 0.75, so 1 month. The same for PB, 1, 2, equals to 4 over 1 times 4, 1 over 4. So this equals to 1 over 16, right? So that's how you get this, 1 over 16 here. Okay? And then, since we know this P equals to 1 over 16, then we want to calculate alpha. So alpha is P times P bar, which is 1 over 16 times 1 minus 16, which is 16 over 15, right? It is 15, and then 16 times 16 is 256. So that's how you get this alpha here. Okay, so that's the approach we use to calculate the activity factor for a circuit. Okay. Okay. Then, so in the previous, we talked about the dynamic power consumption, and the main factor of here is the activity factor alpha. So we show you how to calculate this, like estimate of this, not really calculate the exact result, just to estimate. And then we have the short circuit power consumption. Okay, so when the transistor is switching, the both NMOS and PMOS may be momentarily on at the same time, so leading to this called a short circuit, because they are both on, right? So when this is both on, we have a short circuit current from the VDD to the ground, and this is in a very short period of time, but this also consumes power. So this short circuit power is this short circuit current times this VDD. Okay, so but this is a very short period of time. That's not the main source of the dynamic power consumption. Okay, so this is one of the several examples that we can show you when this is the behavior of the V in and the behavior of the V out and the corresponding behavior of the P and PN, and we can calculate the power consumption according to I over I times V. Okay, so then we can have some kind of idea about the low power design. In terms of the low power design, because we know that we have two parts of power consumption. The first one is the dynamic power, another one is the static power. So we can use two separate approaches to reduce the dynamic power consumption and the static power consumption separately. Okay, and so we can use different approaches. So I give you an overview here, and then we talk about detail later on. So first of all, for reducing the dynamic power consumption, we can use first approach is we call clock gating. So clock gating means we can turn off unused modules. So in other words, we can reduce the value of alpha. So the idea of clock gating is like this, because in the especially in the sequential circuit in modern electronic system, we definitely have the clock. Okay, so for example, we send the clock to the devices like flip-flop or we can say register, and this clock it toggles from 1 to 0 and 0 to 1, right? So the toggling of this clock from 1 to 0 or 0 to 1 consumes power. Okay, so the idea of the clock gating is if certain flip-flop is not used, it's not necessarily we need to feed the clock to that flip-flop, right? If the flip-flop is not used, okay? So the clock gating is, we can have like a gate in front of a flip-flop, and if the flip-flop is used, then the clock signal is passed through this gate, so we can trigger the flip-flop. On the other hand, if that flip-flop is not used, we can use this gate to block the clock signal from the flip-flop. So the flip-flop is not toggled by the clock, so you don't have this 1 to 0, 0 to 1 switching for the flip-flop, and then we can reduce the power consumption. Okay, so that's the idea. Okay. Secondly, as you can see, because the dynamic power equals to C alpha B squared F, right? So if we reduce the alpha, that means we use clock gating. Or we can reduce the capacitance C here. That's true. You can use less devices or more advanced manufacture process. So you can reduce the value of C, so you can reduce the power consumption. Okay, so that's the second approach. Okay, and another very advanced, the idea is run each block at the lowest possible voltage and frequency. That means performance requirements. So that means to reduce V and F. Okay. However, as we mentioned that you cannot always reduce the V or F, right? Because V or F are related to the performance or the speed of the system. So you cannot like unlimitedly reduce the V or F, right? That's ideally you can that's possible, but you cannot do that, because then if you do that and below certain ratio, your performance cannot be satisfied. So there's a kind of like a power management system we call the DVFS, dynamic voltage frequency scaling. Okay, so the idea is we adjust the voltage, VDD, and the frequency according to the workload. So that means if the workload is high, then you increase the VDD and frequency to meet the performance requirement. Otherwise, if the workload is very low, that means not much operation going on, then you can reduce the frequency and the VDD to save power. Okay. This is actually quite a lot used in like laptop. So for example, in laptop, if you this is called idle mode, right? If you don't touch your laptop, or maybe you can adjust the time, like 5 minutes, 10 minutes, then your laptop can get into we call the sleep mode. So one of the things that is done in the sleep mode is to reduce the VDD and to reduce the frequency. And the purpose is to reduce the power consumption. Okay, so this technique is also used in like cell phone. Okay, so if you don't touch your screen on the cell phone, then you get into a sleep mode, right? So this is a quite commonly used approach in modern systems. Okay, so people need to design kind of algorithm to design how to manage this dynamic frequency, dynamic voltage and frequency scale. Okay. We haven't talked about static power, and we'll talk about that later on. But in order to reduce the static power, it's more related to the manufacturer and related to the device. So it's a power gating, so we can lower or turn off VDD for idle module. That's also true. And we use lower VT, the threshold voltage transistor for critical path, or high VT transistors elsewhere. So that means called multi-VT. This is usually called multi-VT technique. So that means you use different devices with different threshold voltages. Okay, so we'll talk about that in detail. And another is we use what we call body bias to raise VT in the idle transistor or to lower VT of the active transistor. So we just dynamically adjust the VT threshold voltage. Okay, so those approaches can be used to reduce the static power consumption. Okay, so we'll talk about those techniques in detail later, and that's the end of today's lecture.